Today you watched two videos, maybe yesterday, about moles. And this is a huge concept in chemistry. This is what we use to count how many atoms are in something, to figure out how many molecules we need to react with other molecules, to figure out how much stuff we can make in a reaction. So this is going to be a theme throughout the rest of chemistry. Before I review exactly what the moles are again, I want to talk about molar mass. Molar mass comes from our periodic table, okay? And it's the mass of 1 mole of atoms or molecules. That's all it is. Where do we get the molar mass? We get it from our periodic table. So right here, I have carbon equals 12.01 grams per mole. And right there you can see on your periodic table, carbon has an atomic mass of 12.01. Yesterday, I explained that atomic mass can be in AMUs. That's a very, very small number. And unless you're a particle physicist, you really don't use it. Generally, chemists use molar mass. This also correlates to the molar mass. Okay, so what are our units? Well, 12.01 also means how many grams are in 1 mole. If I look up hydrogen on my periodic table, hydrogen weighs 1.01. 1.01 what? Peanuts? 1.01 grams per mole, okay? This is a common mistake at the beginning. What are the units for our molar mass? Well, our molar mass is how many grams are in 1 mole. It's grams per mole. So what about if we have a molecule? Let's look at our molecule of water. Our molecule of water has 2 hydrogens, that's what that subscript means, we've already learned that, and 1 oxygen. If I add up the molar mass of every single atom in that molecule, I will get the molar mass of that molecule. 2 hydrogens, HH, and 1 oxygen. I look on my periodic table, I get 1.01 grams per mole, 1.01 grams per mole, and 16 grams per mole. Okay, now I'm all adding this up, and they are in the hundredths, so my answer is going to be in the hundredths, and that gives me 18.02 what? 18.02 peanuts? No, 18.02 grams per mole, and that's for water, okay? Likewise, carbon dioxide, I have 1 carbon and 2 oxygens, grams per mole, 12.01 grams per mole for carbon, 16 grams per mole for oxygen, 16.0 grams per mole of oxygen. So there's my 1 carbon, my 2 oxygens, and that gives me not 14. Where did I get that from? I don't know. It gives me 44.01 grams per mole of carbon dioxide. So if I have 1 mole of carbon dioxide, it's going to weigh 44.01 grams. Salt, I add up my sodium and my chlorine. Now, here is a common mistake, and I want you to ask me, this is C and a baby L. That's chlorine, okay? It's not CI. If it was CI, it would be written C and a capital I. Common mistake because of fonts, that's chlorine. Chlorine is 35.45 grams per mole. Sodium is 22.99 grams per mole. And then I have 58.44 for sodium chloride. 58.44 what? 58.44 peanuts? No, 58.44 grams per mole. Okay, so now let's review exactly what this mole means. When I was in high school, everyone talked about the dozen, and I have to say it didn't help me very much, but it is the perfect analogy, and I don't know any way around it. But when you go to buy eggs at the grocery store, you don't buy an egg at a time. They put them in a pack, and the pack is 12. And the word for 12 is a dozen. Okay, The word for pair is 2. The word for triplets are 3. If I took a bag and put 12 things in it, I would say I had a dozen things. If I had a bag and I put 12 peanuts in there, I would say I had 12 peanuts, okay? So let's look at salt. Here I have this bag of salt, and guess how many atoms I put in this bag? I put in 1 mole of atoms. 1 mole is just this huge number, 6.02 times 10 to the 23rd. That's Avogadro's number. And in this bag, I have 1 mole of salt. Okay? Now, I have another mole of salt. What's in that bag? It's 1 mole. 6.02 times 10 to the 23rd molecules. Actually, it's formula units. We'll talk about that later. We'll call them molecules for now, of salt. And I have a third bag. So I have 3 moles of salt. 1, 2, 3. Each one contains 6.02 times 10 to the 23rd moles of these formula units or molecules of salt. Now, just so you know, 1 grain is not a molecule. You cannot see that tiny. 1 grain is, I think it's a quintillion atoms in there. Okay, so don't be fooled. It's not grains. But in any case, I have 3 moles, and each one contains 6.02 times 10 to the 23rd. So how would I figure out how many moles, formula units are in these 3 moles? Let's take this back. Let's say there are a dozen. In each bag, I would have 12. 3 times 12 is 36, right? But instead of 12, I have 6.02 times 10 to the 23rd. 3 times that is, let's figure that out. So these are our mole conversions. And in each, first of all, how do I know how many atoms I have in there? Did I count every little atom? No, I took the molar mass and I actually weighed these bags. Okay, so, but right now we have 1 mole. Okay, so how many particles of salt are in 3 moles? Okay, well, we know 1 mole equals 6.02 times 10 to the 23rd particles, or molecules, or formula units, whatever you want to call them, right? So I write down my given, which is 3 moles of salt, and I don't want moles of salt anymore. I want particles. And what is my conversion unit? What is my true statement? That's right here. For every 1 mole, I have 6.02 times 10 to the 23rd particles. That's conversion number 1. Now I can also go backwards. I can go from particles to moles, which is flipping those units. And we'll see how to do that in a moment. But right now, our other conversion is going from moles to grams. Okay, up here, we went from moles to particles. Right? Here's our given. There's what we want. Now I want moles. Now I'm given moles and I want to go to grams. Let's do the same problem. I have 3 moles of NaCl equals how many grams of NaCl? Okay, so I start with my given. I always write down my given, 3 moles of NaCl. I don't want moles of NaCl, which is salt. I want grams of salt. Now, For every 1 mole, how many grams of salt do I have? That's the molar mass of salt, right? So that's sodium and chlorine added together. We've already done that. We found the molar mass of sodium chloride, and that's 58.44. 58.44. Okay, so these are how you set these guys up. Let's double check our calculator and make sure we can put this in right. So I have 3 times 6.02 exponent to the 23rd equals 1.806 times 10 to the 24th. 1.806 times 10 to the 24th. Okay, now we always look at what my given is to figure out sig figs. That's 3. That's 3 moles, so that only has 1 significant figure. I underline my 1. Does my 8 round it? Yes, it does. So that would be 2 times 10 to the 24th. Peanuts? No, particles of salt. Particles of NaCl. Okay, down here we do 3 times 58.44, and that's going to give us 175.32. Okay, so I only have 1 sig fig there, so 175, does a 7 rounded? It does. That rounds it to 200, and my moles of NaCl crossed out. I'm left with grams of sodium chloride. Okay, so how do we know all these different units, and how do we keep track of them? Because we are going to do double conversion units. This is where your mole island comes in. So pull this out and let's write in our conversions. And remember, these conversions can flip. How do you know which way they flip? You have to put them in correctly. So grams to moles. This is our, for every 1 mole, I have so many grams. Now, where do I get this gram? Where do I get these grams from? It says right here. It's the molar mass from the periodic table. This is a commonly missed question, okay? Please, please, please look at your mole island. This tells you exactly where to get this information from, okay? If I want to go from number of things to moles, how many things are in 1 mole? Well, for every 1 mole, I have 6.02 times 10 to the 23rd things. And just like all our other conversions, we can flip it, right? For every 1 minute, I have 60 seconds. For every 60 seconds, it is 1 minute. Okay, now, if we do volume of gas at standard temperature and pressure, okay, and we can write this right here, standard temperature and pressure. And we'll get into all those units at another time, but right now I want you to know that this only works at standard temperature, which is 0 C, and pressure, which is 1 atmosphere. You don't need to know that right now. For every 1 mole, it's 22.4 liters. And this is what Avogadro figured out that you learned about in that video. This is how we came up with the concept of this. For every 22.4 liters, there was the same number of particles. Okay, so keep this chart handy and use this. So we are going to do the first problem together on our worksheet. Okay, so if you open up your worksheet, so here is your worksheet. Okay, we have 1-step conversions, which I'm going over now. Your next video will be 2-step conversions. All your answers are down here, okay? You will also be given this worksheet, which you probably will not be able to type on. So you can set this up. You can print this off and write it right in here and take a picture of your work, or you can do your work on paper, but it has to be set up this way. Okay, we need our number, our units, and our chemical. So what do I start with on number 1? First of all, it says to convert to moles. So for our first 1 through 10 problem, my question mark, where do I want to go to? I want to go to moles. Okay? And what do we always start our conversions with? We always start our conversions with our given. So our given is 12.04 times 10 to the 23rd atoms of helium. Okay? Now, do I want atoms of helium anymore? I do not want atoms of helium. And I am converting to moles of helium. So I don't want atoms of helium. I'm going to moles of helium. And this is our conversion chart. You write your given, get rid of your given units, and go to the units that you want to go to. So what do I plug in here? Well, I am given 12.04 times 10 to the 23rd atoms, molecules, electrons, atoms of helium, and I want to go here, okay? So how do I know which way to write this conversion chart? Well, I want to get rid of atoms, and I want to go to moles. If I look right here, 1 always goes with moles, and my atom is 6.02 times 10 to the 23rd. So plug that in your computer or in your calculator and see what you get. Okay, you should have gotten 2 moles of helium on your calculator, but remember I need 1, 2, 3, 4 significant digits. So that is 2 written significant digits. My units are moles and my chemical is helium. So that's how you should be doing that one. Now, I want you to pause this video and see if you can do number 6 correctly. So for number 6, my given is 24 grams of carbon, and it says right here to convert it to moles. So what is happening on my chart? Well, I'm given 24 grams of carbon. I'm at this island, and I'm going to moles. So I need to use this conversion. Here's the problem. People don't know when to use this number versus this number, because I can say how many grams or I could say how many atoms. Grams is a weight. It's something we have to put on the scale to get. Things is a counting thing. If I say how many eggs are in a dozen, you would count 12. If I say how many grams are in a dozen, you'd have to put those eggs on a scale. So make sure you know what they're asking for, what they're given, and so forth, so you know which island to go to. Okay, so I write down my given, 24 grams of carbon. I don't want grams of carbon. How do I get rid of it? I put it on the bottom. I want moles of carbon. So here is my conversion. Now, when people get lost, and they do on a test, all I'll say is put your finger on where you start and put your finger on where you're going to, and whatever's in between there is the conversion factor that you need. Notice 1 always goes with moles. If it's flipped and 1's on the bottom, it's 1 mole on the bottom. 1 always stays with moles. So wherever moles is right now, you put 1. And then I have grams of carbon. Well, where do I get that from? It says right here on my periodic table, that's the molar mass. Right here on my mole island, molar mass from the periodic table. If you look that up, it would be 12.01 grams of carbon. Okay, so when I put that in my calculator, I would get 0.50. Oh wait, sorry, I'm on the wrong one. 2.0 moles of carbon. 2.0. And my unit is moles, and my chemical is carbon. Okay, so now pause and see if you can do 11 and 16. And we're going backwards on our mole island. We're no longer asking for moles. We're asking to go to other places. For number 11, our given is 10 moles of sodium. And it says to convert it to mass in grams. So I'm starting at 10 moles of sodium, and I need to go to mass in grams, which means I'm using this life raft or this conversion factor to get there. Okay, so I set it up by writing down my given. I don't want moles of sodium. How do I get rid of it? I put it on the bottom. They cancel out, and I go to grams of sodium. Where do I get these numbers? Well, first of all, I can see it's flipped, okay? But one goes with moles. So one goes with moles, and grams of sodium comes from the molar mass on the periodic table. And I have that right here, okay? That would be 22.99. 22.99 grams of sodium. So put that in your calculator and see what you get. And you should get 230 grams of sodium. I see what I did here. This should be 10.0. Okay, so I have 1, 2, and that's not a third one unless I put a decimal there, and now I have 3 significant figures. Okay? So, number 16. Number 16 says to convert 3 moles of argon to number of atoms. So I start with 3 moles of argon, and I'm going to atoms. That's a counting thing, so I'm going to things. And here's my conversion factor. Is it flipped or not? Well, I start by writing down my given, 3 moles of argon. 3.00 moles of argon. And my moles of argon cancel. How do I get rid of it? I put it on the bottom, and I want to go to atoms of argon. So what do I put in here? One goes with moles, whether it's on top or bottom. This happens to be flipped. And what goes with number of things? Our things here happen to be atoms. 6.02 times 10 to the 23rd. And that's going to give me 1.81 times 10 to the 24th atoms of argon. Okay, so I have my unit and my chemical. I also have 1, 2, 3 sig figs. I have 1, 2, 3 significant figures rounded properly. Please, please, please do this in class so you can work with me if you're not getting the correct answers. A reminder, your answers are down here, and next I'm posting the 2-step problems.